no slip. You had zero permeability, that means the mass injection was zero, fluid slipping on the surface was zero. You also had a free shear condition. Suppose you have water and air, then at the interface we had the velocity gradient or normal derivative of velocity on that surface. That's there are no shear stresses, therefore the normal derivative of velocity on the surface was zero, free shear condition. If you have two fluids, in general you will have continuity of velocity, continuity of shear stress. All those ideas carry over to the heat transfer problem. ठीक है, नहीं हो रहा है? अच्छा, अभी कहाँ तक? और इंस्टॉल हो रहा है तो करना पड़ेगा, हो नहीं रहा अभी, टाइम लगेगा। तो बाद में इसको इसी को यूज़ करूँगा, तो केवल पेज चेंज करना है ना, दूसरा लगाना। नहीं अभी मैं देख लूँगा। ठीक है, क्या है ये फ्रीज क्यों? अच्छा मैं यही हूँ। हाँ, मैं यही क्यों? मैं दूसरा लगा। अच्छा, okay, that stylus is not working, we have to live with this. So hopefully on Wednesday we are in a better shape. Okay. So to solve the energy equation you need boundary conditions. We looked at several boundary conditions. One is when, let's say, temperature is given, okay, on the surface. Okay, so T given, that's what is written at the top. That's a boundary condition. It's like the no slip condition where velocity is 0, but here temperature is not 0, it's some value. The second possibility is that heat flux is given. So one example that I may give you over email is you have a wire with some resistance, there is some current flowing through it, there is heat generation. So if you have an insulation on top, then with respect to the insulation there is some heat flux going through, which you know, which is volumetric heat generation divided by surface area. That much of heat flux is going out. Okay, so there are many problems where heat flux is given to you. Of course, in the solar problem, you know there is a certain amount of solar flux falling on the wall outside. Inside it is air conditioning. After some time the wall may attain some temperature. Okay, so there is a temperature difference, but the boundary condition outside is solar flux, and that so that's a boundary condition. But you know from Fourier's law of heat conduction that the flux can be related to the derivative of normal derivative of temperature. So essentially it amounts to saying that the normal derivative is given. Okay, that's the second type of boundary condition. If it is 0, it means flux is 0. That's an insulated surface. Okay, it's very much like the free shear surface, where the shear stress is 0. Here flux is 0, that means it's an insulated surface. The third possibility is a convective boundary condition. So that's in fact the most common. You have a solid surface. I gave you an example of this room, okay, where you have airflow here and there is a wall. It could be a furnace of a power plant where you have hot gases inside and the walls will carry tubes with water. Okay, it's water that has to be heated. There's no point just burning the fuel if you don't heat that water. That water will then heat up, will evaporate, will become vapor, high pressure, high temperature vapor, which is then expanded through a turbine to generate useful work. So, the first step in this power plant is to burn the fuel and transfer thermal energy to water. So, the walls will carry tubes with water. So, there is heat transfer, but then on this side, so you essentially you have to solve mass, momentum, energy in the gas phase, and you will have the energy equation in the wall. Like you, I am also hopeful that maybe something will work. Now, last time we said solving this coupled system of mass, momentum and energy in the gas phase and a similar set in the solid portion can become quite tedious. So, there is a handbook route that we follow. This handbook tells you that as a function of the intensity of fluid motion, you can predict the wall heat flux. Okay. You do not know the wall heat flux in units of, let us say, 10 watts per meter square or 100 watts per meter square, but it can be expressed in terms of a parameter called the heat transfer coefficient, which is given a symbol H. In short, it is HTC, it is a heat transfer coefficient, which by and large is only a function of fluid velocity. Of course, it depends on the choice of the fluid also. Is it gas, is it water? It depends on the choice of the fluid and fluid velocity, but does not depend on temperature. Okay, overall, by and large. Okay. So, then the heat flux in the solid phase is minus K S times the derivative of temperature with Y. Now, this you have to be careful while writing the heat flux. It is minus K times the derivative of temperature with respect to the unit outward drawn normal on that surface. Okay, and that unit outward drawn normal will have to be correlated with your choice of the coordinate system. So, here the y coordinate. So, what you see as part of a rectangle is the solid part. Let us say it is heated, and let us say in that example Tf is the far field fluid temperature. In between you have some temperature variation. Because the fluid is cold, that part of the surface is cooled relative to the interior. So, that is the temperature variation. Now, while showing temperature variation, do not put an arrow there. Huh? Temperature is a scalar quantity. For velocity, you show an arrow. Temperature, do not show an arrow. That is a temperature variation. Okay. So, it is hot inside, cold on the surface, and outside is cold fluid. I had this air conditioning system in mind. Okay. The brick is warmed up by the solar flux outside, inside it is cooled by air movement within. The furnace problem, Tf is higher than the slab temperature. The scenario is reversed. So, then that wall flux minus Ks times the derivative of temperature with y. I have aligned y with the unit outward drawn normal. So, y and n are in the same direction, is equal to heat transfer coefficient times the local temperature, that is the interface temperature, minus a reference temperature, which is usually taken as the far field fluid temperature, Tf. Okay. So, this this observation is also linked to Newton. It is called Newton's law of cooling. So, Newton was the one who introduced the heat transfer coefficient, which is very convenient from the engineering perspective, because now H is given to you. So, it is like a given heat flux problem in terms of H. So, if it is intensely moving gases in a furnace, the handbook will give you some value of H. If it is water moving over a surface, it will give you some value of H. If it is water through a tube, it will give you some other value of H. These values are all tabulated. Typical values I have shown here. Usually H will increase with velocity.
Sir,
आगे, अरे थैंक यू. So, h increases with velocity. H may go from 1, h is a positive number, okay, because there is always heat transfer taking place from a lower temperature to a higher temperature. So, h may vary from 1 to 100. Those numbers are all given in handbook. So, it becomes a very useful tool for applying boundary conditions. Called a convective boundary condition. Based on Newton's law of cooling. So, in this, so this is at evaluated at, let us say this is y equal to 0. This is a boundary condition. So, with this boundary condition, you can either solve on the fluid side or you can solve on the solid side. On the solid portion, what is the advantage? Well, u is 0, velocity is 0. Okay. So, these are typical boundary conditions that we use. One is isothermal, one is given heat flux, one is of course, there are 4. Third is insulated, heat flux is 0. Fourth is the convective boundary condition. So, with these boundary conditions, we can now solve the energy equation. Okay, now I have to confess that we are approaching the end of the semester. I was not willing to accept till last week. This week, yes, approaching the last stage, last lap of the semester. So, we cannot be solving too many of these heat transfer problems. Let us look at some simple ones and introduce key ideas. For today, let us assume that it is steady state, heat generation is 0. Let us say we are looking at temperature distribution in a solid medium. So, that velocity is 0. So, that reduces the energy equation to this form. Now, if you have a slab geometry, this is a slab geometry, okay, where this is the material. The left hand side, let us say, is subjected to some temperature T1, the right hand side is subjected to a temperature T2. So, the boundary conditions are given to you in the form of prescribed temperature. Let us say the material has some thermal conductivity Ks. Okay, now, in the absence of any other medium, you may just use K if you wish. So, the governing equation, so let this be the x coordinate, it will give you so del square T is Txx plus Tyy. In a slab geometry, slab is like a wall. So, all the energy transfer is taking place in one direction. If you go across or along in the plane of the slab, there are no variations in temperature. It is called a slab geometry. So, with isothermal boundary conditions across the slab, the distribution of temperature is linear. The solution of d2t dx square equal to 0 with boundary conditions, which you can solve and get this is the solution for temperature. It is a linear variation. Now, it may not be adequate to just get the temperature distribution. Again, going back to the flow problem, what do you do with velocity and pressure? You find forces. So, here you may be interested in finding the heat flux through the wall. So, Q is equal to minus K gradient of T, which will become minus K all in units of watts per meter square. Okay. This K of course is Ks, thermal conductivity of the medium. Because of the linear variation, this Q is the same whether you evaluate. Q will change, like shear stress varies from point to point. Q also will vary from point to point in general, but here there is no dependence on x. It is the same Q going across the slab under steady state conditions. Okay. So, if you want total heat transfer, that would be Q times the surface area. In general, you have to integrate over the area, but here it is. So, essentially we are looking at the this is in vector form, and the result I have written is for the x component. Of heat flux. Let us look at prescribed heat flux boundary condition. So, let us say this temperature is T2, but at x equal to 0. So, this is x coordinate going from 0 to capital L, and you heat the left wall with a prescribed heat flux. So, that temperature will keep going up. You do not know that temperature. What is given is Q wall. The governing equation, so these are only boundary conditions. Governing equation will continue to be d2t dx square equal to 0, x equal to 0 minus k equal to q, and x equal to L, t is equal to T2. So, of course, you know when to use partial derivatives, when to use total derivatives. If t is only a function of x, then it is a total derivative. If it is a function of x and y or x and t or x, y and t, then it becomes partial derivatives. So, the solution continues to be t equal to a0 plus a1x with these boundary conditions. So, minus k a1 is equal to q, and set a0 is equal to T2 minus a1L. So, now substituting back, I have the final solution here. T minus T2, the solution is obtained Tx minus T2 divided by QL over K is equal to 1 minus x over L. This is the temperature variation. So, earlier we had T1 minus T2, so now it is replaced by QL over K. So, QL over K serves as a reference temperature difference that drives a heat flux through the slab. Okay. It's prescribed heat flux. Now, you can consider a convective boundary condition. This is T2, and let us say you have a fluid medium on the left at some reference temperature Tf, and let us say H is the associated heat transfer conditions. That means, the flow conditions on the left hand side are such that there is some heat transfer coefficient H which is available to you from handbook data. So, now you are trying to find the temperature distribution in the slab. Okay. This is a slab of thermal conductivity K. So, the governing equation continues to be d2t dx square equal to 0. Let us write the boundary condition at x equal to 0 minus k dt dn. Now, you realize that n and x are oppositely directed. So, this will be k, and let us use total derivative. Is equal to h t minus Tf. Okay, this is now the convective boundary condition on the left face. At x equal to L, t is equal to T2. So, t is still a0 plus a1x. Okay. So, now you have to substitute these boundary conditions. It's convenient, since there is a T minus T f appearing, it's convenient to introduce a new variable. You can think of it in many different ways. You may introduce a new variable theta, which is T minus T f. Okay. So, then the governing equation is then k d theta dx is equal to h theta at x equal to 0 and at x equal to L theta is equal to theta 2. So, it might be simpler to work with this system. Okay, so, and then of course, in the end you can substitute back for theta as T minus T f. T f is a known quantity. What you do not know is temperature at x equal to 0, you do not know the temperature of that wall, okay, and you also do not know the amount of energy that has gone through the wall, across the wall. So, I will give you the solution here. So, then it turns out that A1 is equal to h over k A0, where A0 is theta 2, which is T2 minus Tf, divided by 1 plus HL over k. Okay, so, these you can substitute back and you get the temperature variation, and then once you have the temperature variation, you can find Q through the slab as the minus k times the derivative of temperature with the appropriate coordinate. So, some remark. Suppose h is very large, okay, h goes to infinity, do I have that? Yeah. Is this correct here? I think we will take those limits a little later. I just wanted to point out in the limit h approaching infinity, T approaches T f. Okay, if h is very large, then the entire fluid temperature is felt at the wall itself. Okay. And if h approaches 0, then it is like an insulated boundary condition. So, here so these two limits. So, if T approaches Tf, that is like an isothermal condition. So, the convective boundary condition contains isothermal and zero heat flux boundary conditions as special cases. Okay, these two can be derived by taking these limits. Okay. Let us take a look at an example of a composite slab. So, a composite slab is one in which you have two slabs 1 and 2 with properties K1 L1, K2 L2 subject to. So, the two of them are brought together, slab 1 and slab 2 are pressed against each other. It is a composite slab. So, this is equivalent to the two fluid layer problem we had studied earlier. So, the governing equations are in material 1 you have d2 t dx square equal to 0 and the same equation in material 2. Okay. Subject to boundary conditions. So, here you have x equal to 0, t equal to t 1. For material 2 you have x equal to, if you set this as the x coordinate, x equal to L 1 plus L 2, t is equal to t 2. These are the boundary conditions known to you. In addition, you will require the second order equation. So, you need two boundary conditions. So, you need an interface condition. So, x equal to L 1, t minus is equal to t plus. Okay, that means the temperature is continuous at that interface. Whatever temperature you have to the left of the interface is also the temperature to the right of the interface. So, here at the interface, where is this is the interface I. At the interface I, temperature is continuous and heat flux is continuous. Okay. So, we have used the temperature continuity condition for material 1 and so for material 2 we use the heat flux continuity relationship minus K to the left of the medium is equal to minus K to the right of the medium. Okay, so, this K has to be this in this. So, to the left is 1 okay, and to the right is 2. So, you have to use the correct thermal conductivities K1, K2. Okay, so, this is the flux continuity condition. So, you can see that in material 1 it will be A0 plus A1x. In material 2 it will be let us say B0 plus B1x. There are 4 constants to be determined from 4 boundary conditions. Okay. So, this will give you the solution and then you can find the heat flux through the slab, through the composite slab. So, I am giving you the final answer. The heat flux through the slab is equal to T1 minus T2 divided by L1 over K1 plus L2 over K2. Okay. So, this is the result you get after solving these energy equations for heat conduction in a slab. Okay. So, at this stage so let me introduce this idea of a thermal resistance. So, we have this result Q equal to minus K times gradient of T, which is this is in vector form. So, Q is equal to minus K T1 minus T2 over L. This is the result we got for a single slab. So, you apply a temperature difference and there is a heat flux. So, that is very much like applying a potential difference and having current going through a current carrying resistor. Stretching that analogy further, we can define a thermal resistance as T1 minus T2 divided by Q. This is a voltage equivalent is T1 minus T2 and the resulting current is Q, V over I, which turns out to be L over K. So, for a slab, the thermal resistance is L over K. Now, if you look at the result we got for a composite slab, we have Q equal to T1 minus T2 over L1 over K1 plus L2 over K2. That is what we had in the previous slide. This was the result we got for a composite slab. Q is equal to T1 minus T2, that is the overall temperature difference divided by the, now you identify L1 over K1 as thermal resistance of slab 1, L2 over K2 is the thermal resistance of slab 2, okay, slab 1, slab 2. So, this is 1, this is 2. You can visualize the composite slab as two resistances in series, and you apply a temperature difference across. So, now you get the flux through the composite slab as overall temperature difference divided by RTH1 and RTH2. Okay. Now, let us look at the thermal resistance arising from convective heat transfer. So, that we will do on Wednesday's time. Just a small announcement that you can collect your quiz answer sheets on Thursday during the tutorial hours. There is no tutorial, but during those hours please go to that room, your tutor will be present, you can collect the quiz answer sheets. I will also be sending your quiz marks, mid-semester marks, and the tutors marks. All of them will be available to you. You can check them up on 16th in the tutorial. Make sure that our records are consistent with yours.